Okay, so we'll start by finishing 3.2. So at the end of class last time, we introduced the notion of a dot product between two non-zero vectors. So the dot product of two vectors, u and v, so I'm going to write u dot v, is defined to be the norm of u, which is just the length of u, times the norm of v, which is of course just the length of v, times the cosine of theta, where theta is the angle between u and v. And of course, remember that theta has to be in the interval 0 to pi. Okay. If either u or v is the zero vector, then we say the dot product is 0. Okay. I won't write that. So it can be a bit of a pain to calculate that angle theta. So at the end of class, I derived a formula for the dot product that's a little bit easier to use than this one. So the formula, so if u is the vector u1, so I'm writing out the components. So u and v are vectors in Rn, and here are the components, Vn. Then u dot v, the dot product, can also be found by just taking the product u1 times v1 and then adding that to u2 times v2, etc. u3, v3, etc. un, vn. Okay, and this formula here is a lot easier to use, although both formulas, so I'll put a star, both formulas are useful, but you just might find one to be more useful at some time than the other. So it's just good to have two formulas to use, and you decide when you want to use each. So I'll give an example. So for example, I'll take two vectors, maybe u will be this vector, and v will be this vector. These are vectors, of course, in R4. Then I could calculate the dot product as 1 times 0 plus 3 times 7 plus 2 times negative 2 plus 7 times 2. So that's 0 plus 21 minus 4 plus 14. So looks like that's what, 31? Okay. In general, the dot product, as I was saying last time, is a measurement of how much two vectors are pointing in the same direction. So when I'll just draw two vectors in R2. When the angle, maybe I'll make one of them. I'm going to see if I can change colors here. Okay. If that's u, and let's say this is v, and of course the angle between them is here, this acute angle. So the angle theta there is acute, meaning less than 90 degrees. They're, somewhat pointing in the same direction. Cosine of an acute angle is definitely positive. I hope you all remember about cosine. So the dot product in this case is definitely positive, okay, because cosine of this angle is positive. So I'll just say u dot v is a positive number in this case, okay. On the other hand, if I had a right angle, so here's u, and here's v, so here the angle between them is 90, the dot product is 0 in this case because cosine of 90 is 0. And just one more example. If u and v are sort of pointing kind of in opposite directions, not completely opposite, but not pointing in the same direction. So again, I'll make u sitting on the x-axis and v, oops, I don't know what just happened. V is over here. Well, then the angle between u and v is now obtuse. Here's the angle theta. Cosine of an angle between 90 and 180 is negative. So the dot product in this case is definitely negative. Okay? So I hope you understand those three cases. Okay. So I also just want to emphasize that you could use the dot product to actually find the angle between two vectors. So because we have, let's just write the definition again. If I wanted to find the angle between u and v, I could just rearrange this formula. Of course, cosine theta equals u dot v over norm u, norm v. And then just taking arc cosine of both sides, allows me to find the angle theta. Oops. Okay, great. So I also want to just point out what happens when you take the dot product of a vector with itself. Oops. So if u is u1, u2 up to un, well, this will end up being u1 times u1, which is u1 squared, plus u2 squared, etc. Right, because you'd just be taking the first component of each of these, plus, and you multiply them, plus the second component of each of these, and you multiply them, etc. So that just becomes this sum of the squares of each of the components. Well, this should look familiar. This is almost the norm of u, except it doesn't have the square root. This is actually just the norm of u squared. Okay, so now for our first theorem. This is theorem 3.2.2. Just a few properties of the dot product. So u v, and w are vectors. And k will be a scalar. So the first property is that the dot product is commutative. U dot v is absolutely the same thing as v dot u. And the second is that the dot product distributes over addition. You might find yourself using this a lot. So if you take u and you dot it with the sum of v and w, this nice distribution happens. This is just u dot v plus u dot w. That's nice. I got a little straight mark right there. Also, if you take a scalar times u dot v, right, so this is just multiplication of two scalars because k is a scalar and u dot v is a scalar. This associates like this, k times the vector u dotted with v. And finally, I'm going to have to go to a new page. Number 4, the dot product is always non-negative. So v dotted with itself is bigger than or equal to 0. This is immediate from the fact that a vector dotted with itself is just the norm squared, as we saw just a few minutes ago. And the only time it's 0 is if v is the 0 vector. So we'll just finish that off. V dot v equals 0 if and only if v is the 0 vector. Okay, so 2 of the proofs are in the book and 2 of the proofs are for exercises, so I am not going to do the proofs for any of those. One extra property that I will just add is that if you take the 0 vector and you dot it with any vector, that's just the number 0. Okay, so I'm not going to do the proofs for those, and I hope that that's okay. Okay, so the last thing that we're going to do in this section is the triangle inequality. So you might notice in this section there are quite a few different inequalities. We're going to do the most important one and omit the others. The most important inequality that comes up and that you'll see over and over again is the triangle inequality. So the triangle inequality is something that you won't be able to get away from. The more and more math you take, you'll just see it come up in different contexts. So what is the triangle inequality? So we have 3 vectors, u, and I'm going to put v going that way, starting at the head of u, and then by the addition of vectors, so I'm positioning these so that v is following u. So to connect here to here, that's the vector u plus v. And the triangle inequality says this, that the vector u plus v, its length is always less than or equal to the sum of the lengths of u and v. So norm of u plus the norm of v. This is pretty intuitive. This is like if you went from your home to school, right? That would be a shorter trip than if you went from home to work first. Well, if you didn't work at school, you worked somewhere else, and then you went from work to school, right? Going from home to work and then work to school would be a longer trip than just going from home straight to school, okay? So this is the principle behind the triangle inequality, and we're going to prove the triangle equality. I'm going to prove this by showing something a little easier. It's always a little bit easier to work with the norm squared, because the norm squared does not have a square root in it, if you recall that the norm does. So norm squared are just easier to work with, but it's going to be equivalent. So I'm going to use the fact that A is less than or equal to B if and only if A squared is less than or equal to B squared. Okay, so you can think about the left-hand side of this inequality, of the triangle inequality, as being the A, and the right-hand side as being the B in my example. So I'm just going to show that A is less than or equal to B by showing that A squared is less than or equal to B squared. Okay, so let's do that. Okay, so next page. I'm going to start off by taking the left-hand side of the inequality and squaring it. So the norm of u plus v squared. Well, as we said, the norm squared is just the dot product of the vector with itself, right? We said that a few minutes ago. So that would be the dot product of the vector u plus v with itself. Sorry. Okay. So now dot product is so lovely. You can just use the dot product here, and I'm going to just do FOIL as if it were actual multiplication. Okay, so this is the same thing as u dot itself plus, well, u dot v. So this is first, outer, inner is another u dot v, because v dot u and u dot v are the same thing, so I may as well just write it as u dot v. And then the last term is v dotted with itself. Okay, so let me just get this stray mark. U dotted with itself is, of course, just the norm of u squared. And then we've got two of these guys, 2 u dot v. And then v dotted with itself is just the norm of v squared. Okay. Now this number here, the dot product, is at most its absolute value, because every number is at most its absolute value. If the number is positive, then it is equal to its absolute value, but if it's negative, then it's less than its absolute value. So a number is always less than or equal to its absolute value. So I'm just going to use that to say that this is less than or equal to the norm of u squared plus 2 times this number is, of course, less than or equal to its absolute value. Okay, and I'm not using anything fancy there. I'm just saying any number is less than or equal to its absolute value. Okay, and I'm using that on the dot product there. So now I'm going to use the Cauchy-Schwarz inequality. So the Cauchy-Schwarz inequality is in the section, but I'm not going to prove the Cauchy-Schwarz inequality. It basically says that the absolute value of the dot product, which is what I have right here, is at most the product of the norms of each of the vectors. Okay, so this is theorem 3.2.4 in the section, if you want to look at that. So I'm just going to use Cauchy-Schwarz here. So this is 2 times norm u, norm v, plus, and I'm just bringing down the norm v squared. This is by Cauchy-Schwarz inequality. Okay? Now look at what we have here. So if you look at this, this looks like something squared. It's like I've got a u squared here, I've got a v squared here, and then I've also got this twice norm u norm v. This is like a cross term. This is absolutely just, whoops, the norm of u plus the norm of v all squared. Just multiplying that out. And there you go. That's the other side, the right-hand side of the triangle inequality squared. So left-hand side squared is less than or equal to the right-hand side squared. So we have exactly what we want. So that's the end of the proof. That's all that we're going to do for section 3.2. I'm going to move on to section 3.3 in the next video.